Hello everyone, let me introduce myself. I'm Sang-Sun the first author of this paper. Since 29, I have been involved in the development and research of battery management systems. Today, I'm going to present the fundamental cause of battery fires. The content of this presentation is as follows. First, we will discuss the issue of low passive cell balance current that pose problem in battery management systems. Second, we will talk about the impact of cell balance issues on series connected batteries. Third, we will introduce the phenomenon of individual cell voltage rising during charge due to differences in aging rates of cells in series connected batteries. Fourth, I will present the simulation results, and finally, I will list the conclusions drawn from this study. I will talk about issues related to the battery management system. When using electric components in series connection, if the value of the components are not the same, an uneven voltage distribution occurs when power is supplied. Batteries cannot be mass-produced with identical capacities. As a result, as shown in Figure 1, an uneven voltage distribution occurs during charging. That's why we perform passive cell balancing. It is crucial to provide a perfect bypass path for the charging current. As the battery capacity increases rapidly, the required current for cell balancing also increases. For fast charging, a passive cell balancing current of 0.5 C rate based on the termination current is necessary. For full charge cycles, a passive cell balancing current of 0.05 C rate based on the termination current needs to be provided. In the past, there have been many efforts to increase the balance current of passive cell balancing. Personally, I conducted research using shunt resistors, and Figure 2 and 3 display the experimental results. Passive cell balance converts electrical energy into heat energy using resistors, which can lead to malfunctions in the BMS, battery management system. When passively balancing the cells with a very low current of 2 ampere compared to the battery capacity, the temperature reaches 150.9 degrees in just 6 minutes, and this was not even during a stabilization phase. Temperature exceeding 125 degrees was sufficient to cause malfunctions in the BMS. When we receive batteries from the manufacturer, they are delivered in a charge state at a specific voltage. After receiving the battery, we go through a sorting process and assemble them by connecting them in series. In this case, the cells of the series connected batteries are assembled with allowed capacity deviation as shown in Figure 1. Since the series connected batteries have a single current loop, all cells receive the same current flow in or out. As a result, during discharge, the cell with a relatively lower capacity reaches 0% state of charge first. Consequently, the cell with a relatively higher capacity retain a higher SOC, leading to SOC variation between cells. Conversely, during charging, the cell with a relatively lower capacity reaches 100% SOC first. As a result, the cell with a relatively higher capacity attain a lower SOC, causing SOC variation between cells. As a researcher, I believe that the different usage languages of each cell in series connected vary will result in varying rate of aging progression. The DC internal resistance of battery varies depends on the state of charge and temperature. As you can see in figure 5, the resistance value is higher at lower temperatures and lower at higher temperatures. And room temperatures and elevated temperatures, the lowest resistance value is observed at SOC 50%, which corresponds to the nominal voltage. As the SOC approaches 0% or 100%, the resistance value increases. This indicates the in series connected battery, the potential difference between cells is maximum at the point of complete discharge and complete charge due to the SOC difference. When batteries are connected in series, it means that there is a difference in capacity and each cell has different charging and discharging voltages. This leads to increase the capacity deviation within series connected battery, causing accelerated aging in cells with relatively low capacity and mitigated aging in series with relatively higher capacity. In other words, the end of life guaranteed by cell manufacturer is based on results obtained under conditions where individual cells are charged and discharged at the same voltage. Therefore, when using batteries with capacity deviation connected in series, the lifespan may become shorter than the guaranteed lifespan. To validate the claims made by the researcher earlier, simulations were carried out using MATLAB. In order to establish a comparison baseline, simulations were conducted under the either condition, where battery capacity were 100% equal. As a result, it was observed that the highest and lowest voltages were the same across all cells. On the left, we have the simulation results for capacity deviation of plus minus 1%, and on the right, for capacity deviation of plus minus 2%. It can be observed that the aging progression of the relatively lower capacity battery number 3 cause an increase in the minimum voltage of the other cells. Furthermore, with a capacity deviation of plus minus 2%, the aging process accelerates even further, leading to a fast rise in the minimum voltage of the other cells. To assess the impact on the maximum voltage, we closely examined the voltage range of battery number 3 from 4.15 volt to 4.3 volt. On the left, we have the results for capacity deviation of plus minus 1%, and on the right, for capacity deviation of plus minus 2%. With a plus minus 2% capacity deviation, the increase in the maximum voltage becomes more pronounced. Furthermore, the rise in the maximum voltage is non-linear, influenced by the capacity decrease in battery number 3. In conclusion, when using batteries connected in series, the risk of battery fires increases. Each cell was found to have the same cycle life, but due to the series connection, the rate of capacity decrease is non-uniform. If the capacity decrease occurred at the same rate for all cells, the difference in capacity at the end of the simulation should have decreased compared to the initial state. However, in both cases of capacity deviation plus or minus 1% and plus or minus 2%, it was observed that the capacity difference actually increased at the end of the simulation instead. I've summarized the simulation results in tables. In table number 1, with a capacity deviation of plus minus 1%, the initial maximum voltage of the relatively lower capacity battery number 3 was 4.164 voltage. However, at the end of the aging simulation, the maximum voltage increased by 35 millivoltage, reaching 4.199 voltage. In table number 2, with a capacity deviation of plus or minus 2%, the initial maximum voltage of the relatively lower capacity battery number 3 was 4.204 voltage. However, at the end of the aging simulation, the maximum voltage increased by 48 millivoltage, reaching 4.252 voltage. These findings emphasize the potential risks associated with increasing capacity deviation in series connected batteries to cut product costs. It demonstrates how compromising on capacity deviation to low battery product costs can be hazardous. In this study, firstly, it was observed that in a series connected battery, each cell cannot have exactly 100% equal capacity, leading to uneven voltage distribution. Secondly, in a series connected battery, the varying charging and discharging conditions for each cell result in different rate of aging progression. Thirdly, it was found that the capacity deviation in series connected battery cause a non-linear increase in the maximum voltage of cell with relatively low capacity, providing a fundamental reason for the risk of fires.